Okay, so I want to talk about a model theory problem, which I've seen as an exercise in certain textbooks, and it's generally given as kind of a first exercise early in the book, but it's actually really hard, or like surprisingly non-trivial. And I wanted to talk about the exercise because I haven't seen it written up anywhere else, or at least I haven't really looked, but you know. But the point is, I think that I can give a pretty good presentation of it, and it's something worth seeing if you're a student. So we all know that if you have two models, A and B, for the same language, if A is isomorphic to B, this implies that A is elementarily equivalent to B. And of course, the reverse is not true because A and B, for instance, can be two models of two different cardinalities, and then they're never isomorphic, but you can obviously have models of different cardinalities of the same theory. But the reverse does hold if they're finite. So the following theorem is what we seek to prove, that if A, and I'll say A or B is finite, and A is elementarily equivalent to B, then A is isomorphic to B. So this phenomenon that the implication can be reversed, it's always true for finite models. And I say A or B because you can express a model being finite in first order logic, so if one is finite and they're elementarily equivalent, then they're both finite. So the proof goes in 3 steps. For step 1, we're going to assume that L is finite. So if your language is finite, this is really easy, because you just take every single relation, every single function symbol, and every single constant in that language, and you write down this big old sentence that represents, all of the structure of the model A. So first off, note that, A is finite with n elements if and only if B is, right? So we can assume they're both finite with n elements. So if L, let's say it has, f1 through fn function symbols, it has r1 through rm relation symbols of whatever arity, and c1 through ck constant symbols. Okay? So now you're going to write down this big sentence that A models. So A models the sentence that there exists x1 through x, and I should use a different n here. So let's just use L, right? We're already using n. So let's say there exists x1 through xn, and I'll just write distinct. We all know how to write that down in first order logic, that they're distinct. And you know what? I'm going to say distinct and all inclusive. This is not standard, terminology, but what I'm saying is there's x1 through xn, and every other x is precisely one of these xn's. So the model has n elements, and these are all n of those elements. And then you're going to write down everything that holds true of those elements. So you're going to say that fi of, whatever x, whatever tuple it is like, x, I don't know, I'm just going to say x star. And this is a big conjunction over the finitely many instances of this function you need. So there's finitely many functions, right? And then that's whenever fi of x bar actually is equal to x star, in the model A. So like, whenever A actually has a function that says that x bar gets mapped to x star, you write that as a sentence. And there's finitely many functions, so you can write this down as finitely many sentences conjoined together. And then you conjoin together all of the relations that hold. So x bar again. You range over all those finitely many relations for every tuple x bar such that in that model, the relation actually holds. And then you do the same thing for, we can just do xi equals c, running out of variables r, so that's 1, for every cr, such that xi really is equal to whatever, whatever CR is in that model. So the point is, this is one humongous sentence, but it completely determines the structure of a model if you have a finite language. And A models that model. A models this sentence. So B models the same. And if you think about it, this sentence specifies the entire structure of A. It specifies the entire structure of B. So this gives you an isomorphism, right? You have this. B models a sentence saying there are these unique elements that have these properties, so you just map the x in A to the corresponding x in B that has the same index. So I think this is the proof people think of when they see this statement. They think of writing down this proof, and it's, kind of trivial, but the problem is L might not be finite. And if L isn't finite, you can't write this sentence down to capture all of L at the same time. And it might not, it's not even obvious, that you have to make that distinction. The first time I saw this exercise, I just wrote this sentence down kind of hastily. And I was like, wow, that's a, fun little exercise. But L could be infinite. And we all know that model theory is, totally open to that possibility. So this is not a trivial exercise by any means to do it in full. So we first need the step where L is finite, and now we're going to make this a little stronger. We're going to expand this to L being countable. So step 2 is L is countable. So how do we do L is countable? Well, this is actually really neat. What you say is L is a union of L sub n, right? This is an increasing union. And let's just say that, I'm just being terse but precise here. We write L as an increasing union, including more and more symbols. And let's just let A sub n be the reduct of A to the language L sub n. We're going to let Bn be the reduct to Ln. Gosh dang it. Okay. So here we go. And so by step 1, so if two models are elementarily equivalent, their reducts are elementarily equivalent, that's kind of trivial. So by step 1, for all n, A sub n is isomorphic to B sub n by some isomorphism. Let's just call that F sub n. So in other words, F sub n is an isomorphism from A sub n to B sub n. And we want to knit them all together somehow into an isomorphism from A into B. So how do we do this? Well, if you think about it, these isomorphisms could be different, right? The isomorphism F sub 1 doesn't have to be like, the same. I mean, they're all maps of finite sets, but it doesn't have to be the same as F sub 2. So the key here is that we still have, right, that A sub n is the same cardinality as B sub n, and they're all n. They're just reducts. We're just restricting the language. We're not changing the size of the set. So these isomorphisms might be changing, but they're still, every F sub n is still, if you think about it, it's essentially, you can interpret it, if you think about it as a map, it's an element of A to the B. And the cardinality of the set of all maps from, or I messed this up, this is B to A. Right, I need to go from A to B. So it's a map, from A to B, but this is just n to the n, which is finite. So there is a subsequence, that stabilizes. Actually, I should write, here's how I should write this. Yeah, I haven't done this proof in a long time. I remember it, but I haven't done it in a while. So I'm just kind of, rediscovering how to write it down. there's a subsequence n sub k, a sequence such that f and k is constantly f. And I should say there's a sequence that goes to infinity, n sub k, such that f and k equals f. So basically, the idea here is you have a finite total possible set of maps. There's only n to the n possible maps. So as you're increasing your size of your language, you're possibly picking up, different isomorphisms, but there's only finitely many total possible isomorphisms between these two finite sets of size n. So if you think about it, f, whatever this constant map that you've cofinally returned to, f has to be an isomorphism from, whatever nk is onto bnk. This is for all k. And since n sub k goes to infinity, we know that that will eventually involve all symbols in our language. So this constant map f must be an isomorphism from a onto b. So essentially, the heart of this argument is the pigeonhole principle for infinite to finite. So that does it for a countable language. The final step, step 3, is for arbitrary n. Arbitrary L, a language of arbitrary cardinality. So in particular, uncountable cardinality is what we want to look at here. So if your language has arbitrary cardinality, then the idea is we want to reduce this to a countable language. And I'm going to have to think about this because I don't remember exactly how this step goes. I think it is relatively straightforward and easier than what we just did. But basically, let's see. How do we step it down to countable? Well, I don't think we're going to write L as a union. I mean, you can't write it as... it's a union of countable languages. It's a union of finite languages, but it's not like an increasing union necessarily of countable languages unless it's like, omega 1 or something. So we can't just do that. Well, here's what we do know. For every countable, let's call it L prime, subset of L, we know that the reduct of A to L prime is isomorphic to the reduct, not of A, but of B to L prime. That's step 2. And I think this has to be the key. So for every countable sublanguage, the reducts are isomorphic. So we get some isomorphism for that reduct. Oh, of course. Yes, so the key here, right, the key is that A and B are still finite of size n, right? So if the models are finite, then if this language is uncountable, then you're way over specifying the amount of information. So there are only countably many interpretations for function symbols, relation symbols, and constant symbols. So what this means is that, so actually, for some countable L prime, not A, L prime, we have that the set of all, I don't know how to exactly say this, but basically all the function symbols, relation symbols, and constant symbols that have interpretations in L have an equivalent interpretation in L prime. So basically, for all f in L prime, there exists, gosh dang it, for all f in L, there exists an f prime in L prime such that the interpretations are the same. Right? And same for relations and constants. And thus, since we already know that these models are isomorphic for L prime, this countable language, this implies that they're isomorphic for the entire language. Right? Because if you're isomorphic for L prime, but L just has copies, basically, of things in L prime, then the same isomorphism works. And then we're done, right? We're done. We've, satisfied the theorem for an arbitrary language, so that's the end of the proof. So yeah, as you can see, it took me a little while. I struggled a bit to remember how to do this arbitrary case. This really is not an easy problem, and I think I saw this in Chang and Keisler. I don't remember if it was a starred exercise. I actually have the book right next to me, and I'm going to look up if this exercise is starred or not. I have a feeling it wasn't, and I think it should have been, especially appearing early on in what is potentially the first book in logic you're going to read. It is definitely an exercise deserving of a star, in my opinion. So this would be... So in Chang and Keisler, this is proposition 1.3.19, and that's the converse, I should say, because it states in proposition 1.3.19 that the converse of isomorphism implies elementarily equivalence is true for finite models. And that is an exercise, I think. Yes, this is exercise, or proving the proposition is exercise 1.3.4, and it's not starred. So I think that it is deserving of a star. It is definitely a tricky exercise. You have to, first realize that you have to, go through these cases. And the only proof that I know of goes through all these cases, and each case has its own trick, right? For the finite, that's the obvious proof. But for countable and uncountable, you need these two different tricks. And it's really not something I think a beginning logic student might even realize you have to do. And if you do realize it, it's still a little tricky to figure this out. So anyway, I just thought I'd show you this trick. That's all I have to say for today. So take care.